There you go.
Okay, thank you very much. So good morning, everyone. I'm Ralf Klesen from Würzburg, and happy 14th of July. Mark promised us that we will not be interrupted by any more fireworks. Let's see if it happens. And let me shortly introduce today's speaker, Ulrike Diebold from the Technical University of Vienna. That's also where she did her PhD in 1990, and then the following 20 years she spent in the US, first as postdoc at Rutgers for 3 years, and then the following 17 years as professor at Tulane University in New Orleans. Before she came back to Austria, to Vienna Technical University in 2010, as a professor or chairholder for surface science. And that is exactly also her scientific profile. She's working mostly with scanning tunneling or scanning probe techniques on surfaces, surface science, surface chemistry, in particular on oxides. And she will talk about this today. And she found a very nice renaming for a surface, namely the solid vacuum interface. Please, Ulrike, the floor, or rather the screen is yours.
Hey, thank you. So let me try to share my screen. All right. Okay, and let me press and also start my slideshow. All right. You can, let me move this over here. All right, so you can see my screen, you can hear me?
Yes.
You can see my cursor. Yes, so thank you, Mark, and all the co-organizers for organizing the Les Houches Summer School. I was really looking forward to being in the Mont Blanc area. Hasn't worked quite out, but at least a little bit. And I'm very happy that I was invited. I mentioned before that I've listened to several of these talks and learned a lot. I hope that I also can contribute something, and then the audience and the students listening in can learn something from me. So the whole summer school, of course, is about interfaces. And very many of the people who have spoken before me have talked about interfaces between two different oxides. Now, I want to talk about this interface of a material with nothing else. So the solid vacuum interface, i.e. the surface. So that's our perspective. And the perspective we are bringing in are a little bit different because also I'm a physicist and very interested in physical phenomena. I must say that most of our money comes from chemistry. So we put in a little bit of chemistry perspective. In fact, most of the work that we've been doing on very similar materials that have been discussed here already have been motivated by their chemical properties. Now, I know how it is to listen to these talks, and I don't know how it is with you, but I sometimes get quite impatient. So I've put here in the bottom the actual outline of my talks. So there will be 3 topics. After somewhat introduction, I will talk about potassium tantalate and surface polarity. Then about strontium titanates, I will focus on these 2 materials, perovskites, and then in the end, I will talk a little bit about very practical thing about homoepitaxial growth, epitaxial growth, which is really essential to make this, to fabricate these oxide-oxide interfaces. And then I've prepared 61 slides. I don't know how that will work out with the allotted time, but here you can see how far along we are. All right, so without further ado, let me try to go down how I do this. Oops. Okay. So yeah, I think I should introduce my co-workers or co-authors, I should say. This is the whole surface science group in Vienna. We are in the middle of Vienna. This is the Stephansdom right in the center of town. And this is top of the roof of our physics building. Michael Schmid is my colleague and the co-lead of the group. And the people who have been doing the work is really two postdocs. One is Martin Sedwin, who just became a professor at Charles University in Prague, and the other one is Michele Riva. And they worked with two students. Michele worked with Jade, and then Martin worked with Igor. So we're all pretty much experimental. But one nice aspect of the work that we are doing is that it interfaces very nicely and intimately with theory. And we had some nice talks in the beginning about theory, first principles or density functional theory. And Vienna is really mecca of that. So some of the best codes have been written here. So we collaborate with Cesare Franchini from the University of Vienna, and then his postdoc, Michele Reticcioli. So those are the people who were involved in the work. All right. So I put this slide to kind of give you a perspective where we are. So this is, I think, is some sort of this this picture, or maybe a similar one you have seen quite a bit, since this is about emergent phenomena at interfaces. So we have these oxides, and these oxides can have a strong interplay between the charge, orbital, and spin degree of freedoms. And because of that, you have a lot of very interesting physical phenomena. So this is really the center of the whole workshop. And then one prototypical example that has been discussed in the literature a lot, and also I think has been mentioned here quite a bit, is this very interesting interface between strontium titanate, which is a band insulator, and lanthanum aluminate. And when you put those two together, then it turns out that there is some electron accumulation at this interface. And in a picture that is often ventilated in the literature, you can look at it as a consequence of polarity. So the lanthanum oxide is real layers that have an essential charge of 1 plus per unit cell, and lanthanum aluminate -1, +1, -1. So this would be the charge, +1, -1, +1, -1. And then because you have planes, first approximation, infinitely large planes with a certain charge, you also have fields. And because of these fields, then the potential accumulates, it diverges. And as in response to that, then electrons start to flow at this interface, and then these electrons have very interesting properties. So if you followed me so far, there's one thing you should remember, because it's really essential for the rest of the talk. So in this case, where the charge of the unit cell is plus, minus, +1, -1, the thing that happens is that exactly half an electron per unit cell flows to this interface. Okay, it's important that it's exactly 1/2. It's easy to show. I will not show it. That could be a nice homework or a nice exercise with really at the summer school. But if exactly 1/2 of an electron per unit cell accumulates here, then you have a field that's half, instead of 1 in one side, you have half on one side, half of the other side, half one side, half the other side, and then the potential goes up and down a little bit, but it doesn't diverge. So this is also called an electronic reconstruction and leads to this interface metallization. So what I want to talk about today is, actually, maybe you can think of it, I've split it in half. I'm talking about a similarly polar material, not lanthanum aluminate, but potassium tantalate, that also has this property of plus, minus, plus, minus. And I just want to see or show you what happens at the surface, okay, without this other strontium titanate underneath. And then so this is the first part of the talk. The second part of the talk, I want to talk about strontium titanate, and I want to look at this interface with the vacuum, so just the surface. So that's the kind of outline, if you like, of my talk. As I mentioned in the previous slide, I had a lot of little symbols of the people who give us money. They give us mostly money because of chemistry. And it turns out that many of these materials, perovskites, are also very interesting in surface chemistry. So depending on how I'm doing in time, I might then show you in the end also a little bit about an interesting reaction that is very, very important technologically. Okay, so still the introduction. So let's start. We will talk about perovskites today. That has been introduced in several of the lectures before. Just a reminder, in the simplest case, you have a cubic unit cell. You have so it has ABO3, that's the chemical composition. A is the cation at the corner of the unit cell, for example, strontium or potassium. B is the cation in the center. It's surrounded by an octahedron of oxygens. And the size of the unit cell is 4 angstrom. Now, the interest in these perovskites is, of course, because they have a very wide range of compositions, and because of that, a wide range of physical properties that we talked about before that are tunable. And the wonderful way of tuning these properties is to build these superlattices with epitaxy. And then, my interest is also the solid state chemistry. So the reason why you can form the superlattices is because most perovskites have a similar crystal. They all have a similar crystal structure. There's more or less some distortions that are very interesting, but in first approximation, they're all cubic with some distortions, and they all have about a 4 angstrom size. Okay, and because of that, you can pack them really nicely in this superlattice type fashion. So 4 angstrom from here to here, and then I am a surface person, so I like to think in terms of layers. So if you want, you can think of this one as, if you think of it of continuously repeated in 2 dimensions of an AO surface, so potassium oxide, for example, and then 2 angstroms underneath, there is a BO2 tantalum dioxide surface. So if you go from half a unit cell, then of course you have 2 angstroms. So what I want to talk about today is to see what's going on with scanning probe microscopy. Okay, so that's what we do. We use, so again, these 2 concepts, surface polarity, and then in the end I want to talk about strontium titanate. But let me move one more slide in my way, and let me talk about the experimental techniques that we're using. So we use, as Ralph mentioned, scanning probe microscopy. So the probe is here. This is a small needle. So to give you interest, give an idea about the size. So this would be like 1 millimeter from here to here, or something like that. So there is a small needle, a wire, typical tungsten wire etched to a sharp tip, and that is our probe. And the probe is then, the whole setup here is mounted on a scanner piezo, so you can move this probe in X and Y direction, and also in Z direction. And then, oops, sorry. And then you can move it in X and Y and Z direction, and then you'll have some sort of signal. So in scanning tunneling microscopy, it's the tunneling current between the tip and the sample. When the tip is very close in tunneling distance, so half an angstrom or so, in front of the sample, and you measure the tunneling current either from the sample to the tip or the other way around. And that gives a very sensitive measure. You can image surfaces with very high resolution. Now in this particular case, this tip is mounted in addition on this tuning fork that resonates with its own resonance frequency, about 20 kilohertz or so. And when the tip comes close to the surface, it experiences, close means really close, so like chemical distance, half a nanometer. So that the very end of the tip, that is 1 atom, already interacts with the surface kind of chemically. So in the van der Waals regime, or sometimes even in the chemical regime, we almost make a bonding. And then this interaction between the tip and the surface gives you force, and the gradient of this force causes a frequency shift. So this is the non-contact AFM STM. So you have those 2 signals, you have the current and you have the frequency shift, and those together give you really wonderful information about the properties of these surfaces. Now, in order to really probe the surfaces by themselves and not any sorts of contaminations, this tip and the scanner assembly is mounted inside of this cryostat that one can cool down to 4 Kelvin. If you would look through this camera, you could see this tip. And then inside of this chamber is very low vacuum, so less than 10⁻11 millibar ultra high vacuum that keeps our samples clean. And we do this imaging and then we combine it with spectroscopies, X-ray photoelectron spectroscopy in my lab. Sometimes we go to synchrotrons and do ARPAs, low energy electron diffraction. It will be a little bit important in the later part of the talk where I can see the periodicity of the unit cell and also some low energy ion scattering. So this is one of the tools that we have in the lab. And in the first part, when I talk about potassium tantalate, this was done on this machine, which incidentally hangs on this bungee cord assembly because, you know, I showed it before, we are in downtown Vienna in a very busy intersection with the subway underneath, we're in a high rise. So we have this little gadget to keep the tip in front of our sample without too much vibrations. All right, so non-contact AFM stem in ultra high vacuum. I said that it's a wonderful technique to look at surfaces. So let me show you an example, not a perovskite here, a much simpler binary oxide, rutile, titanium dioxide. Okay, so the samples that we use are typically single crystals. So this would be several rutile titanium dioxide single crystals, about 2 millimeters in size, little cubes. Rutile titanium dioxide has a band gap of 3 electron volts. That means that visible light cannot be absorbed, so it's transparent to the eye. One thing we need to do in order to probe our surfaces is not just keep them under clean conditions, we have to clean them in the first case. When they come into the vacuum chamber, they're pretty dirty, so we usually do argon ion irradiation and heating that restores the damage that is caused by this argon ion irradiation. And because of that, we introduce some vacancies. So we actually remove oxygen from these samples, all oxide samples, it happens. Because of that, if you remove oxygen, you make a VO in Krüger-Fink notation, a vacancy at the position of an oxygen atom. So you create an oxygen vacancy at the surface. And oxygen, I think that's been mentioned before already, right? Oxygen formally has a 2- oxidation state, so 2 extra electrons. If you remove the atom, these 2 electrons stay behind. And these 2 electrons are given to the sample, so they dope the sample in type excess electrons. Okay, so this is a model how the surface looks like. So we have these oxygens that are 2-fold coordinated on the surface, titanium that's 5-fold coordinated on the surface. So it's octahedral in the bulk. And then when you look at the non-contact AFM image, you're very close with the tip, you oscillate it, and you look at the frequency shift, and the tip interacts with this oxygen. There's a repulsive interaction that causes a frequency shift. If you plot the frequency shift, you can see each single oxygen atom that sticks out here. This is done in constant height mode, and then here's a hole as expected, right? So here is an oxygen vacancy. So you can directly see these defects in a very nice way. So that's one thing you can do. You can look at how morphologically the samples look like at the atomic scale. And of course, you can also look at the atomic structure. So if you park your tip that I explained before here somewhere, and then if you ramp the voltage between the tip and the sample, so typically the sample voltage, so 0 here, and then you go to negative sample voltage, positive sample voltage, negative sample voltage, positive. You measure the tunneling current, or here actually it's the derivative of the tunneling current. then you can see essentially, if you like, something like the density of states. So there's a small band gap here. There's the empty states. This is where a tunnel into the empty states, positive bias voltage, so electrons are sent into the sample. Here, electrons are coming out of the sample. And then actually there should be a 3-volt band gap, but there are some states here. And these states happen to be polaronic states. So these are electrons that are localized on single titanium atoms. So if you measure the tunneling current by moving the tip, you can see here are titanium atoms. You cannot directly see the vacancies. Here are titanium atoms. And here, these are the electrons that have this particular binding energy. Equally well, oops, sorry. Equally well, you can look at the, instead of looking at the filled states, you can look at the empty states, that's here, and in empty states, you can actually see that each oxygen vacancy in its surrounding has changed the electronic structure a little bit. So there's a lot of information to be gained from doing this scanning probe microscopy. Okay, so now we want to apply this technique to a perovskite that is a polar perovskite. So that's what we want to do next. And in fact, the experiment we will do is really simple. Okay, so we take a sample, this potassium tantalate, we stick it in the ultra-high vacuum chamber, then we cleave it, so we break it in half, and then we look, and then we heated it a little bit to see what happens, and then we looked again, and then we exposed it to water. So this is the outline of the experiment that I want to show you. And what I want to point out is that, okay, in the beginning I mentioned that when you have a polar oxide, right, then the electrons are flowing to this interface. That's one way this polar catastrophe can be relieved. It turns out that's not the only way. So in surface science, these polar oxides have been keeping us busy for quite a while. I want to point out this nice review article by Claudine Nogueras that was published in the year 2000, where she enumerates all the different, what we call polarity compensation mechanisms. So anything that prevents the system from building up and accumulating a diverging potential. So I already mentioned that we can have the surface states, electronic reconstructions. There can also be some physical reconstruction, rearrangement of atoms. There can be some intermixing. There can be some defects, adsorbates, and so forth. So all these things can happen, and all these things, it turns out, happens on this potassium tantalate when we go to this different, preparation regimes. So that's what I want to talk to show you now. All right, so next slide. This is again what we talk about, potassium tantalate, cubic perovskites, as mentioned, 4 angstrom between these 2 layers, 2 angstroms in between. It is also a wide bandgap semiconductor, similar as titanium dioxide, so 3.3 V. Now that's more interesting for me than for you perhaps, but these tantalates have a very high quantum efficiency for solar water splitting. So that means you shine sunlight, you take water and out bubbles hydrogen, which is a wonderful fuel, with a quantum efficiency of 56%, which sounds great. Each photon, 2 photons are converted into 1 hydrogen molecule. That's really great. Unfortunately, only the photons that I absorbed, so very little of the solar spectrum. But it's something that excites me as a half chemist. It's an incipient ferroelectric. You had a long lecture about ferroelectricity already, so just as a reminder, in a very simplified way, so if you have a cubic unit cell, in these perovskites, there's no ferroelectricity, but you can have this ferroelectric distortion, essentially a change, so a distortion, orthorhombic change. So in a simplified way, this central cation here, in this case tantalum, would move either, let me see if I can do that, move either up or down, right? So that would be polarization in one direction or polarization in the other direction. Not normally, but if it's an incipient ferroelectric, so if you do something with the system, then you can push it towards this ferroelectric distortions. For example, if you dope it with niobium. All right, and as I mentioned, it's polar along this 001 direction. So the layers of KO plus 2 minus, so net charge 1 minus per unit cell, tantalum dioxide 5 plus 2 times 2 minus, so plus per unit cell, 1 charge per unit cell, plus minus plus minus. So if you just stack this, if you just take a material like this, you stack it, you build up this enormous potential across a millimeter size sample. All right, so that's our system. This is how our samples actually look like. So we got them from a collaborator, Lynn Bodner. They're not transparent because they're doped a little bit with some dopants, barium, copper, ytterbium for N-type conductivities. We can do nice STM. They're pretty big. We put them in, we hold them from one side and we hit them in, meaning inside our outer high vacuum chamber that I showed you before. We hit them with a blade, we yank them, and then they cleave, and then we look at what's left behind. Okay, so what would one expect if one cleaves a sample like that, right? So normally I would ask you to think about it for a moment. So I can only ask myself. What you would expect is that half of the crystal is gone. In fact, that's what you would expect, I think. I would expect, right? So you have these layers of tantalum oxide and then KO islands, or perhaps the other way around. So that's the case. So look at this large scale STM image, scanning tunnel microscopy image. What you can see is, you can see 250 nanometers in size, pretty big for us. You can see these worm-like features. When you take a line profile, you can see that these little worms are 2 angstroms higher than these terraces. So you have something, you know, an island, either a potassium tantalate island, on top of it a KO island, on top of a TaO2 terrace, or the other way around. It's difficult to say, right? And you know, it's fairly straightforward to measure the area. It turns out that you have half, the surface is half filled with these islands, right? Which kind of makes sense. Remember, I told you in the beginning that you have to remember that in order to alleviate this polar catastrophe, you need half a charge per unit cell. So if you have only half of the surface covered with either positive or negative island, then the overall polarity is compensated. So you have alleviated this polar catastrophe. That's really like the trivial case. So, you know, it makes sense that half of the surface is missing. And that immediately tells you, okay, I don't have this problem anymore with this polar catastrophe because I have either half negative or half positive islands here, half of a full layer. Right? So we can measure, that's the case. So that's nice. That's, you know, like the trivial case. But there's a little bit more, right? So there's a little bit more. So first of all, before I go to a little bit more, we can find out if this, what's left are KO islands or tantalum oxide islands. Because we have our nice atomic force microscopy, we can just look at the crystal structure here. We can take atomically resolved images. If it's KO, then it has the square lattice. If it's tantalum dioxide, then it would look like this. It turns out that KO islands are left behind. So when you cleave it in half, you cleave it like this. So you break this bond between tantalum oxide and KO, and then you also break the lateral bond. All right, apparently it breaks easy in this direction if we have KO and in the tantalum dioxide. All right, fine. So we have half of the charge here compared to before. We know it's KO, but there is, as I mentioned before, a little bit more. So we have islands that are small. Overall, half the charge is missing, but we have these negatively charged islands that are 3 to 8 nanometers in size. This is what we measure. Okay, so there is still quite a bit of electrostatic potential laterally. In Z direction, overall, it's compensated, but laterally, you still have quite a bit of potential. And it turns out that there is still some electrons, and these electrons are confined, so they're pushed away. So a little bit like a quantum dot, they're pushed away from these KO islands to the center, and then you have still these electrons that accumulate here. Either they come from the fact that we have some dopants in our system, or it could also be that those are electrons that flow here to compensate for the polarity in this small region, right? So this is the kind of sketch. And then here in the next slide, I show you the experiment. So this is again a large scale, not as large as before, but pretty large scale scanning tunneling microscopy image. So that's taken in constant height. So you move across, the thing that sticks out are the KO islands, right? They're a little bit higher. And in between the dark regions are the tantalum oxide terraces. And this has been taken with a very small bias voltage where electrons flow from the sample to the tip. So the sample is negative. So those are electrons, the field states. Then you can see here, this is the outline of the tantalum oxide. Here you can see some electrons, directly see the charge with this particular energy, this particular voltage. Interestingly, there is some quasi-particle interference patterns, but they're only in the center of these terraces. So here, they're not present. And if you look, they're really not present, because if you look and do some scanning tunneling spectroscopy, so you park your tip here, you can see a KO island with a very large band gap, right? Fermi level here, large band gap. If you are in this region, then you also see a band gap, no states in the tantalum, in the tantalum oxide region. But if you're in this region, then you can see there's a lot of things going on. So there's lots of quite interesting states in this region. And not we, but Phil King, a number of years ago, did exactly the same experiment. He did ARPES on this sample, on a cleaved sample. And then he saw these subbands. And then he attributed these subbands to this spin orbit splitting of this potassium tantalate. I'm wondering, in fact, if the subbands are not because of this confinement, this lateral confinement between these KO islands. Right? So that's what we have. When we just cleave, half of the KO goes away, and then on the tantalum oxide terraces, these electrons accumulate here. All right. Now, this situation happens, but it's not the thermodynamic ground state. So this is just cleaving it, so at low temperature. So we were wondering what happens when you give the system a little bit of mobility so it can go and readjust and take the lowest energy configuration. So we just took the sample and heated it. Here first to 312 Kelvin and then looked, and then to 341 Kelvin and looked. What happens is, remember, so we have these islands, KO islands, that still have quite a bit of electrostatic potential laterally. In the center, the highest one, what happens was that here oxygen vacancies started to form. So if you have oxygen vacancy, the oxygen goes away, the electrons go away, so it's a double plus charge. So these oxygen vacancies are positively charged. At the center of these negatively charged islands, at these temperatures, the oxygen cannot yet desorb into the gas phase. It just moves, it just migrates from the center of these islands to the rim. You can see that actually. You can see there's oxygen vacancies in the center of the islands, and there are these extra atoms at the borders. If you heat a little bit more, you see more of these oxygen vacancies, or in the middle, where you have the highest electrostatic, negative electrostatic potential. That's where good positive charge is expected to accumulate. And here you can see that the oxygen accumulates at the rims. So oxygen vacancies form in response to this surface polarity. We call it the compensation mechanism number 3. All right, so this was heated a little bit above room temperature, not very high yet. So let's heat a little bit more, and then let's lift the kinetic barrier. Maybe there is an even more favorable configuration the system wants to take. So that's done here. So here we heat it to 387 Kelvin. You can already see that it's really clear that there's some lateral rearrangements, right? So the KO islands, they start to get holes and redistribute on the tantalum oxide layer. And then if you heat even hotter, then this thing forms, right? So this is an STM image, AFM image, 20 times 20 nanometers. And here you can see nicely, these are still the KO islands with the nice square symmetry, but they're very narrow, right? So nothing, no material has been lost, it has just rearranged. And then looking at, when we got this result, we were really quite puzzled, but actually in retrospect, I thought, okay, this is of course what must happen, right? If you remove half the charge, then in Z direction, you prevent this accumulation of this diverging potential. But in XY direction, if you have big islands, you still have quite a bit of electrostatic potential. If you make this island smaller and smaller, then you will also make this potential that accumulates in X and Y smaller. But at some point, you know, it costs energy, it costs steppage energy to create these steppages. So at some point, you can't go push that forever. At some point, there will be an offset between the electrostatic energy versus the energy that it costs by making, each time you make a steppage, you break some bonds and it costs some energy. And in fact, that can be calculated with density functional theory. So this is, on the left side is kind of our model. So this would be a striped face with a width of 1, 2, 3, 4, 5 atoms of KO islands on top of tantalum oxide terraces. This is our unit cell repeated in X and Y in periodic boundary conditions. And then one can change this, so one can make this width smaller or wider and calculate the total energy of the system. So if you start with a very wide terrace, the total energy is high. At some point, there is a minimum at 5 atoms in this stripe. And then at some point, the surface energy goes up again. And this is because it costs these steps. It costs extra energy to create these steps. The electrostatic potential is constantly decreasing. So from a high electrostatic potential for a wide stripe with 12 atoms here in this direction to virtually 0 when you go down and you make these stripes smaller and smaller, so they essentially distribute. Now this has, if you, another interesting aspects of this, so this was a nice confirmation of what we've seen before, that these stripes that I showed you before, they are pretty much 5, give or take 5 units, 5 atoms in width. But, you know, in very good agreement what this density functional theory calculations tell us. Now, if you look at, this is the slab from the side view. So that's the, what our theory friends use. So GGA and VASP, the symmetric slab. And they changed the width of these KO islands. Now, when you look closer, it turns out that there's also quite some bit relaxation. So underneath of these KO islands, there was an upwards relaxation. And where the KO islands are missing, there's a downwards relaxation. So remember, I showed before this B cation moved up and down, and then it used some polarization. So it seems we have some, I'm not sure it's ferroelectric because in theory we can switch it, but we have some distortions that are reminders of electricity, just because we create this inhomogeneous surface with a titanium oxide termination and a KO termination. Now, this is the electronic structure calculated with DFT. Here's the Fermi level. The band gap is a little bit too small, which is typical for this functional that was used. The empty states is mostly tantalum 5D. This is the oxygen to p valence band. Here is the interesting aspect. And then if you look at the projected density of states, the partial density of states of this labyrinth structure calculated for different widths, for 4 atom wide, 10 atoms wide, and 12 atoms wide. If you have one stripe that has quite a bit of width, so there's a big electrostatic potential. In green here plotted is the tantalum dioxide partial density of states. In red is the KO density of states. And then for a wide island, so wide tantalum oxide terrace, this potential moves this density of states down. If you zoom in, you can see here really are some electronic states that are pushed below the Fermi level. So these are the states that we have observed with scanning tunneling spectroscopy before, to just be at this these islands that have a wide width. Remember, when we were at the islands with a smaller width, they were not there because they were pushed away. All right, so you have this beautiful labyrinth structure with a very, with positive and negatively charged, small positive and negatively charged, self-organized domains. If you think like people who give us money do is in terms of photocatalysis, for example, where you shine a photon, you excite an electron hole pair and you want to separate them, this would be pretty much ideal. So this would be really helping with separating charges, and then this charge could do chemistry. For example, the hole could help with creating a hydrogen, reducing a water molecule to a hydrogen. So is that okay? Let's just put a little bit of water. We can do that by opening a valve on our ultra-high vacuum chamber and leaking in a little bit of water vapor and see what happens. And what happens is this. Okay, so this is an AFM image. Here is still a KO island with a normal structure, and here we have some sort of different structure that looks nothing like before. This is has a 2/1 periodicity, so in electron diffraction you can see this would be the spots from before. Here are these extra spots. So something happened to our nice labyrinth. What happened? Well, I show you what happened. So it turns out that the water really reacts quite a bit with these potassium oxide islands. So if you put water down, first we have these KO islands here on top of this tantalum oxide terraces. it reacts and makes them mobile. So it distributes this KO across the surface. So it kind of laterally resolves them and distributes them. So this is the structure that we get. We get KOH stripes in 2 different directions with a 2x1 periodicity. It turns out that adsorbates can also compensate. So negatively charged OH hydroxyls on the positive charged islands also can act as a polarity compensation. So we form an adsorbate overlayer in the end. So this beautiful labyrinth structure I showed you is really not stable. Once you expose it to humid air, it will form this distributed KOH type of overlayer. So not great for electron hole separation, but kind of interesting from another point of view, because if you take this surface where the KOH is distributed across uniformly, and we heat it to 250 degrees C, then water desorbs from the surface again. We get our labyrinth. If we expose it to water at room temperature, then we distribute the KOH again. So this means these are really 2 different types of equilibrium structures. So depending on the environment, either the labyrinth or this KOO overlayer are the most stable surfaces. So these are really 2 equilibrium configurations, right? Now, because this is both are equilibrium configurations, one can do some what we call, we can create a phase diagram. So this is a DFT derived surface phase diagram. That means that you calculate the surface energy and then you look at what kind of chemical potential, in this case of water, you have the lowest energy configuration. So here is the chemical potential of water. Here is the surface energy in electron volt per unit cell. And these different lines are for these different configurations. So this is for the hydroxylated overlayer. The more water you have, the less water you have, the lower the chemical potential, the lower the surface energy, the higher the surface energy. And at some point, at this particular chemical potential, this striped phase with different widths would take over. And then this chemical potential of water can be converted. It's dependent on the pressure and the temperature. So when converted into pressure and temperature, and one can see at which point one of these two configurations has the lowest energy. So one thing maybe I want to point out is that I showed it before, this density functional theory calculations for different widths of these stripes. So with 5 atoms or 2 atoms or 12 atoms, you can see that the change in width doesn't change the surface energy a bit as much, but when chemistry comes into play, then the surface energy is lowered quite dramatically. So chemistry in terms of energy wins over here as opposed to physics. Okay, so we're almost done with this first part. This polarity compensation mechanisms on potassium tantalate. So it cleaves easily, it forms these KO islands that I showed you. It removes half the charge. In between, on these tantalum oxide islands, we have band gap states that are laterally confined. We also have some ferroelectric distortions, one direction underneath here and the other direction underneath here. This is just when we cleave it. This is all happening at the as cleaved surface. If you give a little bit of temperature and can go to the more preferred state, you form oxygen vacancies. by moving oxygen around. At some point, you restructure the whole surface to this labyrinth structure. And then if you put water, it dissolves laterally and gives you this hydroxylated surface. And then you can switch back and forth between these two equilibrium configurations. All right, so this was the first part, potassium tantalate. So we are halfway through of our story on slide 30. Now, let me switch to the next part, right? Let me switch you from potassium tantalate, which is an intrinsically polar material, to strontium titanate. So let me go here. So this was, we talked about this polar material. Now let's talk about this strontium titanate. And what I want to show you here is that if you just take this surface, okay, if you just take a strontium titanate surface, and then remove this half layer just by itself, this is not an equilibrium state. It turns out that on this surface, you have all sorts of reconstructions, not electronic reconstructions, but actually massive structural reconstructions. And you can change what kind of structures you have by changing or adjusting the surface stoichiometry, so the strontium to titanium ratio. All right, so strontium titanate, I think, has been coming up quite a bit, either as an interesting material by itself, or remember we talk about emergent interfaces at oxide-oxide interfaces, right? We are built up in a nice Lego brick way, this one monolayer of one material or 2 or 3 layers of this other material. And very often this is done on strontium titanate 001. It's a very cheap, well controllable substrate, also for this building up of this 2-deck material, lanthanum aluminum strontium titanate interface. The way it's normally prepared is you go to a favorite crystal vendor, you ask for a quotation, they sell you strontium titanate wafers in any form and shape in 001 orientation. And then when you just cleave them, you would end up with half strontium oxide, half titanium oxide, right? But you can actually, turns out you can etch off this strontium oxide and you end up with only titanium dioxide. So 3.9, almost 4 angstrom step height. This is by soaking the surface in water and then followed in a buffered HF solution. You get this really nice stepped surfaces, all titanium dioxide terminated. And people have used that extensively for growth, especially for growth of these interfaces, right? Now, I know this works really well. And the problem from the surface science community is that even though this is titanium oxide terminated and this has this right step, you know, the actual top layer of this titanium oxide, of these wafers that you can either buy or etch, looks really, from a surface science perspective, pretty horrible. There have been papers published by several people that showed that normally when you etch it, some fluorine stays behind. You can, instead of etch it with fluorine, you can also just etch it hydrothermally. So you can just kind of cook it in a pressure cooker and water vapor. Then you don't have this problem, but you still have some carbon, and you put it in the system, and then you heat it up in oxygen to get rid of this carbon. You end up with this beautiful terraced structure. You end up with, in diffraction, a 1-by-1 lead pattern, but these surfaces, from an atomic point of view, are not as well ordered as you would think. They're not just completely bulk terminated, right? And we know because we have looked at them, and they look like a pretty horrible mess, I must say, both in terms of composition, but also in terms of structure. So I want to show this in the next slide. This is a surface that has a 1-by-1 lead pattern, so it's bulk terminated. So these are the spots that you would expect if not much happens, no physical reconstruction. If you heat it up, not much changes. If you heat it above 600 degrees, then you will see extra spots for structural reconstructions. This is typically the temperature people need to heat to get rid of the carbon. So this is an ash-cleaved surface. I will show in a second how we do that. We have a wonderful, nice atomic resolution, very flat surface. If we heat it up, the surface starts to make monatomic holes. If we heat it more, you know, there's small islands at 500 degrees, small islands, pretty flat. But if you look, the actual atomic structure has really deteriorated. This is more like an amorphous structure, I would say. And then if you heat it up more, then these reconstructions start to form. Okay, so this is a caution for people who look at these etched surfaces from a surface science point of view. They are not as nice, wonderful, bulk terminated, 1-by-1 terminated as people like to draw in their figures and people like to calculate in their density functional theory calculations. All right, well, let me talk about this one here, strontium titanate induced surface polarity. So strontium titanate by itself is really not polar. So you have TiO2, strontium oxide, TiO2, strontium oxide layer. So there is no accumulation of electrostatic potential. But what I will show you is that we can induce this polarity by cleaving. Okay, let me before I do that, let me step back a little bit to what I told you before. So this is, even though we're already now here at this strontium titanate story, I want to show this image that I showed you before, similar from before. This is ash-cleaved potassium tantalate that we discussed right at length the last half hour or so. So these are these KO islands, right? Let me put away these stripes that I put. So these are these KO islands. I showed you they're really, really funny, right? So here are big steps, 2-3 monolayer height steps, and these KO islands, like a carpet, float across them. That's kind of a really strange thing that you would have something like a ceramic material floating across a step, okay? Really strange. So we were wondering why that is. And then we came up with this idea. So remember, we cleave our KO, right? By just yanking it with a blade from the side. And it's an incipient ferroelectric. So we were thinking, okay, perhaps during this cleaving, what we do is we have some sort of polarization domain, ferroelectric, so polarization domains, where this B cation is moved up a little bit or moved down a little bit. So I have a polarization in one direction, a polarization in the other direction. If you have that, you start cleaving, then you have here a long bond, and here you have a short bond, and here I have a long bond, and here I have a short bond, depending on the polarization domain. So we came up with this idea that perhaps during the cleaving, what we have here, it cleaves along this domain. So in the crystal itself, this is, so to speak, the imprint of these polarization domains. So that's what we thought perhaps happened. So when we submitted the paper, we got nice reviews, but the referees all said, well, you know, how come it cleaves so funny? And then we put in this hypothesis, and it didn't really believe us. Was published anyway, but then we thought, well, let's see let's see if that's true, right? Let's see if that's true. Let's see if that's true by trying to induce this polarization. Let's try to cleave something that doesn't cleave well. So it turns out strontium titanate by itself, okay? If you try to cleave strontium titanate, it doesn't cleave as nicely as potassium tantalate. It just breaks apart. There's been many people who've tried to cleave it before, published some nice papers about it, but it's really stepped. There's not this nice, you know, terraces of one kind of the other. So they say, let's try to cleave strontium titanate and induce some ferroelectricity, right? So ferroelectricity, it's an incipient ferroelectric, similar like potassium tantalate. You can induce the ferroelectricity either by doping or by external strains. I said, okay, how about we put some external strains? We press it from the side. We press it from the side and then it elongates in one direction, and then we have some polarization, and then this B cation moves up or down a little bit. We induce some polarization domains, and then we can cleave it, and we will have cleaving depending if this is moved up or down. We end up with either if it's moved up in strontium oxide terrace or if it's moved down at titanium dioxide terrace. So that was our idea. So Igor did that, and he said, okay, let's take a strontium titanate single crystal, polished 110 direction. So the top is the 001. Let's squeeze it from two sides, and then let's squeeze it and cleave it. Okay, so that's what he came up with, and that's the little gadget he built. So these are sample holders. It's hard to see, but in here, this is two parts. This is the lower part, this is the upper part. In here is our strontium titanate sample that normally doesn't cleave very well. Up here, he put a little bit of an ear so he can grab it with the wobble stick. There's a little gap in between these two, and then he had some just screws, so he tightened that really well. Now, you know, we did some finite element calculations later, and it turns out it actually should be possible because the strain you can induce in this material, but just, you know, tightening an M2 screw is not enough to induce ferroelectricity. Luckily, we just experimentalists and just tried, because it turns out it works really well. Okay, so this is a cleaved sample. You can see this is a wonderfully nicely cleaved sample. There are some big step heights, 2-3 nanometers high. They all run in some directions, but if you then do scanning tunneling microscopy, you see this is wonderful super wide terraces that have never been observed before, really. Normally when people cleave it, they just get this, you know, messy stuff. Even more so when we land our STM tip at different positions, we could see 4 angstrom step train. So going from one, remember 4 angstrom is the size of the unit cell I pointed out at the beginning, from one to the next, so it's always the same termination. And then we had to move several core steps, and then we ended up with strontium oxide terminated layers, right? And actually, you know, we cannot scan large enough to see the boundary really. So we took the sample out and we looked with scanning electron microscopy. It turns out that when you have a TO2 terminated and a strontium oxide terminated surface, then the work function is quite different. You can see that as a contrast in the secondary electron emission. You can see here, this is 50 microns, okay? You can see here one domain of strontium oxide, titanium oxide, we don't know which one. And then the domain walls really run across crystallographic direction. So it cleaves really super easily. So we really think that what we do is we induce these ferroelectric domains that are really sizable during the cleaving by confining the strain. Okay, How do we know that this one is TO2 and that this one is strontium oxide? Well, again, we can just zoom in and do atomic force microscopy and STM. So this is the strontium oxide. And the perfect terraces, you can see a nice square pattern. Nice square pattern. We have functionalized our tips, so we know which one is an oxygen, which one is a strontium. So these bright dots are strontium atoms, and there is also some defects, some vacancies. There's clearly some missing strontium atoms, just regular positions. And then if you do STS, you can see, like potassium tantalate before, a wide band gap. If you go to the other side here and then zoom in, this is constant height imaging. So you cannot see the lattice in between so well, but what you can see is there's some dots. And we think that these dots, they have exactly the same density as these missing atoms here. And if you look, zoom, so we think these are actually strontium atoms. And then if you look here, there's again some interesting electronic structure on the as-cleaved system. Again, some electrons that are donated from the strontium, extra strontium atoms that put some density of states here near the Fermi level. So why do we think that way? So we think we yank it apart. We either have the titanium oxide on one side, strontium oxide on the other side, on one domain, on the other domain, the other way around. And the sum of the strontium stays behind, left over on the titanium oxide. And it turns out there's always a certain amount, always 14% of these point defects exactly within the error bar, exactly the same on the two domains. And the reason is, you know, because we induced this ferroelectric distortion, we induced some polarity, right? And if we induce some polarity, we would end up with this polar catastrophe. But by leaving behind some of these extra point defects, we alleviate that. And these extra point defects make this diverging, normally diverging electrostatic potential and bring it down to a sort of like up and down configuration. Okay, so we can cleave these surfaces. We can make nice domains of one and the other. They are one by one terminated. But it turns out when you heat it up, the whole system starts to intermix. And at some point you start to form reconstructions. If you heat high enough, strontium will evaporate from the surface and you end up with a titanium, mostly titanium terminated surface. And now I want to come to the last part. I think I have about 10 minutes, so maybe I will make this a little bit shorter than planned. I want to talk about this surface reconstruction. So different surface structures. This is not a strontium titanate 110, 001 that we talked before, but the 110. But a very, very similar phenomenon happens on all low index strontium titanate surfaces. So the 001, the 111, and the 110. So it turns out when you heat it high enough, so the system can assume its equilibrium configuration. Like I showed before, when you cleave the potassium tantalate, you end up with some sort of configuration, but if you heat high enough, the surface will assume a different lowest energy configuration. It turns out that the lowest energy configurations for all strontium titanate surfaces are these surface reconstructions. So that means a different surface symmetry. So different surface symmetry. So symmetry you can best see in electron diffraction. So these here are the spots that would be here for a bulk terminated 110 surface, so rectangular 110. They're always here circled. And then in between you have extra spots. extra spots in reciprocal space, means a bigger unit cell in real space. So these are these reconstructions, 1, 2, 3, 4, 5, 6 extra spots in one direction. These are, and then when you take a surface and you heat it and sputter it to remove remove carbon and other contaminants that you have on the surface, you end up with one of these reconstructions. And then you can switch. These are all equilibrium structure. You can switch back and forth between each of them. Like before I showed you potassium tantalate, you can put water or dissolve it. It goes back and forth. Here also can switch between all these different surface phases by adjusting the surface composition a little bit. So when you start here and you deposit a small amount of titanium, so this would be 1.9 monolayer, and you heat at high temperature, typically 600-700 degrees C in oxygen, depending on how much titanium we put, you can get all these different reconstructions in different periodicities in diffraction, and in real space you can also monitor them in STM. You can go one way by putting titanium, and you can go the other way by putting strontium. So there's a whole phase diagram with the surface structures, and it turns out that's true for all the perovskite we've looked at, that at equilibrium, when you change the surface stoichiometry just a little bit, you form a whole zoo of different, reproducibly different, reversible surface structures. Okay, so why is it interesting? Well, let me talk a little bit in the end about, we're now here at epitaxial growth, okay? So I think we had some really nice talks already about MBE growth that came out of the Schlom's group and other people. What many people use is pulsed laser deposition. So you hit a target, polycrystalline target with the laser, then you ablate the material, you have some sort of background gas, typically oxygen, that slows it down, you grow it on a substrate, and here can do nice epitaxial growth. So I want to talk about just homoepitaxial growth. So it's really not very useful. It's just about the growth mechanism itself. So you take strontium titanate here as a substrate, you take strontium titanate as a target, remove stuff from here to here, and we change the laser fluence and the background gas and the substrate temperature and all the things to adjust for nice homoepitaxial growth. So that's what I'm going to talk about in the last few minutes that I have. Okay, so we do this in this ultra-high vacuum chamber where we have a combined pulsed laser deposition and surface analysis. So here's the laser. Here, ultra-high vacuum chambers, they all coupled together. In order for epitaxial growth, you need to monitor with reflection high energy electron diffraction. I'll show in a second why. We can take our sample and slide it back and forth and look at STM and diffraction and all sorts of other things, everything ultra-high vacuum, and then really monitor the growth with this read. It's the standard method that people use quite a bit. But we can also look with scanning tunnel microscopy. Okay, so let's read reflection, high electron energy diffraction. Just as a reminder, you have your substrate. You come with an electron beam, 30 kilo electron volts or so. You reflect it off the sample. You have a diffraction pattern. You look at the directly reflected spot, and then you sit here. You do your deposition either by MBE or in our case with this krypton fluoride laser with pulsed laser deposition. And then you deposit, and while you deposit, you see this read oscillation. So this is the real time. You grow one layer, second layer, you can count. At some point you stop. And the reason why this works is really quite simple. You have a beam that's reflected. If your surface is smooth, you have a high intensity, you've tuned it to such a case. If you have some islands, then this electron beam will be just dispersed. So the intensity will go down. If you have many islands, half a monolayer full, then will be at minimum. If you grow more, it will go up again. At some point, you have a nice flat surface again. And then you have the first oscillations, you have the first layer completed. So that's what people use quite a bit, okay? So we can follow this step by step. So here we have a large scale STM image, is a monatomic step of our nicely prepared surface. Here's the read intensity. We put one pulse. We have islands. We can count how many. We do 2 pulses. We have more islands. 3, 4 pulses, more islands. So it's half monolayer now, something like that. We put more, it grows nicely together. More nicely together. So we can really monitor what I've showed you in the cartoon now in real space. So here we have already 1 layer filled. It's a little bit too much. We have the second layer coming on again. Okay. Now, because we do this nice STM, we can actually remember these steps, right? This presence of the steps disperses this electron beam. So we can actually just count the steps, right? So that's an easy thing for us to do. So we just measure how much step length we have as a function of pulses, and oh, something is not right, right? So it should be at the minimum here after 5 pulses, but is not. So we're like, oh, what's going on? Okay. Is this read picture wrong? Cannot be, right? That's been used quite a bit. So it turns out that here, in between these islands, if you zoom in with high resolution, you can see there's another kind of structure. And if you then also include in your measurement these steps between this structure and this structure, then it follows exactly a read. So what happened? Well, what happened is, you know, that this pulsed laser deposition, you put whatever you have on your target from one side to the other, stoichiometrically is not always right. It depends very much on the laser fluence. You can have incongruent ablation. It depends on preferential scattering in the gas. You can have all sorts of things that change so that you have less one component here than the other here. So if that happens, you change the surface, you go from, right, I showed you only a little bit of change in strontium or titanium will move you along this phase diagram, right? If that happens during your growth, you end up changing your surface. And that's the case. So here you have a nice strontium titanate substrate. We grew, and this growth was a little bit, just a little bit of strontium rich. So we went from one type of phase to another type of phase. So we went from this 4x1 and 5x1 to 4x1, 5x1 with a little bit more, okay? So it turns out that when you do that, and you see how much of stoichiometry accumulates, you can actually really sensitively, we published in this paper, really sensitively measure how much off stoichiometry you have. Mm-hmm. Well, why would that be important? Well,
Ulrike, just to let you know, we're going into overtime now.
Okay, yeah, I'm just almost done. Why is it important? Well, if you're slightly strontium rich, that's okay. But if you're slightly titanium rich, you go from one phase to the other phase. So here you can see this 6x1 phase, and it turns out, or 2x4 phase, and it turns out that on this particular surface, the material doesn't stick as well. So clearly see there's more material here than here. If a mixed surface accumulates in one side, and what you end up with is with homoepitaxial growth, exactly the same configurations, just changing the, in this case, the laser fluence a little bit, you end up with not a nice, wonderful growth, but with this really deep holes in the surface. Okay, so Yeah, thank you. I had a lot of stuff, but I think I'll skip that. I want to go to the last slide. Here's the summary. I've shown in length about this polarity compensation on potassium tantalate. I've showed you how we can cleave strontium titanate. In the end, I've showed you how the surface reconstructions can sensitively tell you how off-stoichiometric you are during growth, and how you can also explain why the growth doesn't proceed as nicely as you want it to be. That's it. So if there's any questions, I'm very happy to answer them.
Thank you very much, Ulrike. I'm almost always amazed at the atomic resolution that you can achieve on these oxide surfaces. I mean, atomic resolution on SDM is not so rare. You can get it easily on metallic samples, but on oxides, it's really a challenge. And I always wonder if you use a special kind of oxygen in Vienna. Okay, anyway, we have already one question I see here on the chat. There's a second one coming. First question is by, let's see if I can open this correctly. I think this was by Ulrike. Do you want to pose this question yourself? You can open your mic.
Good morning, everyone. My question concerns the preparation of the strontium titanate 001 surface. Mm-hmm. You showed really nicely that the water soaking and the BHF etching does actually produce an ill-defined surface. So I was wondering, for us as film growers, do you have experimental advice how we could maybe get a little bit better defined surface when we start doing the PLD or MBE?
So the short answer is no. We try now. I'm actually amazed that it works so well, right? So I mean, our experience is that these imperfections float up during the growth. So when we start with when we do a slightly non-stoichiometric growth, like here, okay, it turns out that somehow the material goes underneath and this top layer just floats up for the most part. That's what we see. Not all of it, but most of it. I think that's the reason in our thinking, that's the reason why, even though you have a not perfect top layer, you can still form this, I mean, there's no question that it works, right? You can still form these nice, beautiful things in between. My concern is a little bit that not everything floats up. So for example, if you etch with HF, it's pretty clear from, you have to be very careful to do that, but it's pretty clear that there's some fluorine left behind that also will not be burned away with oxygen. And I'm wondering how much of this fluorine stays behind when you grow this LAO-STO interface. That would be my concern. Can I give you better advice on how to make it better? Not really. We're trying to do that now. So we actually we're trying all sorts of etching methods. Look at things. The problem is, as soon as we put it in vacuum, as soon as we start to heat it to a temperature that is reasonable and we remove the oxygen, even at high pressure, we start to form these surface reconstructions. So the good news is that it floats up, but how? I think it's more a concern if you really look at the surface itself, right? People have looked at this 2-deck of clean STO materials. There I would be very worried about what you actually have at the surface. Did I answer your question? Not really.
Ulrike, you're happy?
Definitely. Thank you very much for your honest answer.
Okay, next question is by Gal. You want to pose yourself?
Yeah, sure. Can you hear me?
Yes.
Yeah.
Okay, so thank you for the great lecture. It was very interesting. So I wanted to ask about, you showed in the potassium tantalate case that when you soak it in water, the surface changes. You also mentioned something about creating hydrogen when you shine light on it and also soak it in water. So in STO-LAO and also in doped STO, if you shine UV light on it, it is persistently photoconducting. And there is this work by Jeremy Levy group that they show that when they soak it in water, the resistance goes up dramatically, and it's like a reverse effect to this photoconductivity. So I wanted to ask if you did anything, any work on STO, maybe STO-LEO when exposing to light or when exposing to water, and see how the surface changes, maybe have some more insights on this phenomena of persistent photoconductivity. Or
so that's an interesting question, actually, because so what we have done is, so on this cleaved STO, actually we're doing these experiments right now on this cleaved STO, right? We have these domains with one polarization and the other polarization. And then when we shine light, we can clearly see that there's some electron-hole separation, so that the electrons go one direction and the hole go the other direction. We can tell that by Kelvin force probe microscopy. So that's the pristine surface. What happens when you expose to water is, and that's true not only for this KO, I think that's true for any AO terminate perovskites. So these AO terminated surfaces are very, very hygroscopic. They're very, very interact with water quite fiercely. So I think you would always end up with something like this under humid conditions, right? So how exactly it works, I think you have to do a very well controlled experiment, but certainly the fact that the water is here and dissociates and make these OH groups changes the surface chemistry, and because it changes the surface chemistry, I think it also changes the electronic structure quite a bit.
Okay. Okay, and if I can ask just a follow-up question, do you think that just by taking, let's say I make this interface, just by taking it out of the chamber and exposing it to atmosphere and some UV light and something like that, a lot of the effects I and everybody is measuring is related to interaction with some humidity in the air?
I think so, right? There's been this work, I'm not so familiar, but I think there's been work by Jochen Mannhardt and people where they've shown that you can, you know, really write things with an AFM tip, and that the environment matters a lot, because you also have some electrons on charge donation by these adsorbates, and they really interact with the electronic structure of the substance.
Yeah, I think it's also by the Jeremy Levy group.
Yes, yes.
So okay, but thank you. Thank you.
Okay, are there further questions? Maybe I can ask one myself. And this concerns the mess that you find with STM on the STO-001 surface for samples that have been prepared with this HF method.
Right.
I see the mess in STM. I totally believe that. But if I do a lead pattern experiment on the surface, I get very sharp spots. And if I then start growing LEO on top of it, as for example, and then look later at the TEM pictures of the cross section of the interface, everything looks sharp.
Yes.
So my question is, how thick is this mess layer? And what happens when you start continuing with epitextual growth on top of it?
So I think this mess layer is one layer.
You
know, I think it's just really one layer or something like that. So what you see is really one by one. You see the thing underneath, right? You see the one by one of the substrate underneath. I mean, there's this. So the interesting thing is like strontium ruthenate, right? There's this nice paper by someone that says strontium ruthenate is like gold because it's one by one. Well, strontium oxide terminated strontium ruthenate, I can tell you no, it's not. It's kind of one by one, but because nothing changes, because the strontium oxide is so reactive. So you have some sort of stuff on the surface. And underneath, I think, is a perfect lattice. And but the only way, I agree with you, it works really well. So I think the only way it can work is that you kind of shuffle the thing and it floats up like a surfactant on top of it. And then you end up with these sharp interfaces that you can see in lead and in TM. I mean, it works, right? The only thing is, I don't know how much stays if everything floats up, that I don't know, right? How much stays behind? But I can tell you that the starting point, even though you have these wonderful things, the starting point from a surface point of view, and that I've been puzzled by this too for a long time. From a surface point of view, it really is not great. And we always thought, well, maybe you cannot get the atomic resolution on STO for some reason with STM, but we can with AFM. And if you have a perfect surface, you can perfectly see it. But if you take any of these edged surfaces, you have a nice lead pattern, but the surface is a mess. And if you heat it up hot enough, at some point you start forming these reconstructions, mainly because strontium evaporates. And then you end up with a titanium-rich surface, and all these reconstructions have titanium-rich surfaces. And I don't know, maybe it even helps that it's a mess, because as I showed you before, when you have a certain kind of reconstruction, you change the stoichiometry a little bit, you change the structure, and then having a different structure on different patches on the surface really makes the growth worse. So, in the end, it works, right? I'm really amazed why.
I'm glad I never did STM before my actual PLD growth, because I never would have proceeded if I would have seen the surface. There's another question by Si Zhao. A follow-up question. Do you want to open your mic? Or maybe I can read it. So it's a follow-up question of the previous question. So I can expect the STO valence be changed during an XPS measurement. Can we also connect some reports regarding with STO substrate surface superconductivity in a vacuum to what you have showed surface reconstruction?
I'm not sure I understand the question.
So I read if
STO valence induced by the XPS, or I don't understand quite.
Si Zhao, do you want to explain your question? See if I can. The mic is open, but we don't hear you. Now it's closed. Sorry, Mike. Okay, so what do you mean by the XPS question? If the valence changes during XPS?
So is he or she typing, or?
Because of the X-ray.
Ah, okay. So it's synchrotrons, right? That's what people have been doing. So what happens is when you shine intense X-rays, so not with a lab source, but it's synchrotrons, what you can make is oxygen vacancies like here. Or actually on TO2, you can also see them nicely, right? I showed in the beginning, you have these oxygen vacancies. Because of the oxygen vacancies, they dope extra electrons. And these extra electrons then can form something like either polarons or two-deck gas. Is that what you mean? So on TO2, it's known that for these oxides, they're quite sensitive to irradiation. When you shine very intense light, there's something that's called the Knottel-Feynman mechanism, that you kick out oxygen. And by kicking out oxygen, you form these vacancies. The vacancies donate the electrons, and depending on the system, you can either form a polaronic state like here, so deep in the gap, or sometimes you just form a state here, a coherent state right next to the Fermi level.
I will actually be talking about this on my lectures on Thursday and Friday. Right. But this is not related to the mess that you observe on the surface.
No, I don't think so. No, I think a chemical mess. So some contaminations is, if they had fluorine there, probably fluorine, carbon, and then just some. I mean, I've shown before that you can have all sorts of different structures, right? And I think it's just some. What I meant with mess was, so this If you look at these surfaces that I showed before, when we heat, we start with a well-defined cleaved surface. We heat up and we form something that's still pretty flat, but ill-defined structurally. But underneath, you still have this one by one. If you look at the XPS, it looks dead on. It looks exactly the same in lab XPS. So not inducing these oxygen vacancies by default. Looks exactly the same. There's no pinning or any sort of change. The spectra look exactly the same.
I see there is a question by Ulrike to me. If we see an extra layer on top of LAOSTO in our STEM pictures, well, that's difficult to answer because the way we prepare our lamella, it's difficult to maintain the integrity of the very surface in the electron microscopy. At least we have not really looked at this in much detail. What I can tell you though is that when we do XPS and in particular angle-dependent XPS on the LAOSTO system, we typically do not observe any strontium or titanium signal on the surface. So I know that some people have seen that and have reported this, but there may be details in the PLD process that may be responsible for this. But that's something that still needs to be debated. Yeah.
I don't know where this one layer goes. That's a mystery for me.
Yeah, yeah. As long as people still have more questions and can type them in, I have one question on the KTO system in the early part, where you showed these electron patches that you have on the residual free tantalum oxide surface. Actually, two questions on that. You had this. Right, I have to move this window away. You show this as the local DOS on these patches. You made this comment that you wonder if the subbands that Phil King has seen in ARPIS may be not related to the spin orbit coupling or spin orbit splitting of the bands, but due to I guess quantization in these patches. On the other hand, in the ARPIS experiment, you do see that you have a formation of a band. You see momentum dispersion, and that you can only have if you don't have quantization, right?
That's true. I don't know.
And the patches are relatively large.
Yeah, we don't have dispersion here. So when we change this, we can look here at dispersion. It seems that this pattern doesn't change actually. So I don't know. I don't want to interpret this. Also, I must say that in his experiment, I think he also did this, that he was shining light longer to make these oxygen vacancies, right? If I remember correctly.
Yes,
so which we don't, right? When we don't have any oxygen, we make oxygen vacancies later.
Yes.
Here, but only laterally, right? By reshuffling the oxygen from inside out. So yeah, maybe it was not a qualified comment. I shouldn't comment on other people's work. I know that he has cleaved it, but he also has put these oxygen vacancies. So I can tell you that we've looked at this quasi-particle interference pattern and we don't see dispersion. So it's actually quite interesting also how it interacts with molecules, what happens here on the acid cleaved surfaces, these larger patches.
And then you show in this DOS picture, local DOS, you have the zero bias anomaly.
This one here, yes.
At zero bias.
So
do you want to comment on this?
No, because we tried to go after it and it was really not so reproducible. I mean, it's not so, it's a little bit tricky, right, to do zero bias STM. So
you see it all the time, and it's
so not so clear exactly what it is. So we're looking more. So these are different. The black curve is taken from a different experiment. So I mean, same experiment but with different settings on the DIDV, on the lock-in, so that it can have a little bit higher resolution. Why it is it? I'm not sure really. So we're looking at all sorts of things. You see, what we think now is actually, but that's still work in progress, is that some of this thing is interesting. This is switching peak. So when you ramp up and down this peak, which has a strange shape, changes polarity in one direction and in the other direction. So something is switched, but it's high bias voltages. So I can clearly switch those things around.
Okay.
And then we have also this polaronic peak here. We think that's a bipolaron. But what exactly happens here, I am not sure.
Okay. So Gail is asking another question. Gail, please.
Hi. So I wanted to ask, there was this paper 2 years ago published in Physical Review Materials about SRO and TiO2 terminated STO-LAO interfaces, where they claim that the terminating layer of the LAO is always aluminum dioxide, whether if it's TiO2 or SRO terminated. Did you have, by any chance, some experiments checking the terminating layer on STO-LAO interfaces for the P-type interface with the SRO termination?
We have not done any of this LAO growth on top of it. So I just cannot answer the question now.
Okay.
We have not looked, we have looked at, recently we've looked at LSM, lanthanum strontium manganate. You know, each time, because we do it so carefully, time takes a very long time for us to grow one material. In the end, we can grow it really perfect, but we haven't done any of this LAO STO yet, no.
Okay, I see.
So now I cannot answer this question.
Have you ever tried to do STM on bare LAO, or is it too insulating for that?
It's too insulating, but we could now with the non-contact AFM. So the we have now published some papers with the non-contact AFM on completely insulating, like sodium iodide, which has a really wide band gap. So that's the nice thing. So I'm really excited about this non-contact AFM, because I think that's really the technique we've been waiting for in oxide surface science, because you can see both the electronic structure, filled state, empty states, and also the actual atoms, right? You can actually see an oxygen vacancy as a vacancy. The thing you need to do is you need to functionalize this tip appropriately. So that's, I mean, we spend way more time preparing the tip than the surface. So for this, for example, we have to functionalize the tip with one single oxygen atom. And then so people have been functionalizing with CO and other things. So with one single, then you get this wonderful resolution. You can see each oxygen vacancy. But LAO, no, we haven't yet. I think it's really interesting thing to use.
Mark's telling us that our time's up, but there was one question by Ulrike. How do you carefully approach the tip in the non-contact AFM mode? Maybe you can briefly answer that.
Yeah, so you can do that with just turning on the feedback. So if you have a conducting material, it's easier. You approach it with the STM mode. If not, then you have to approach it with, you know, just really slowly and look at it, look with the frequency feedback.
Okay, then thank you very much to Ulrike and to all other participants. So this concludes this morning's session, and I hope all will be back later this afternoon. Thank you very much.
5 p.m. 5
At 5 p.m. 5 p.m. today.
Thank you.
Okay. Bye-bye.
Bye.